Welcome back to Organic Chemistry. We're continuing on with our discussion of alkenes, and we're going to start looking at the reactions of alkenes. In this subsection of the video, I'm only going to discuss electrophilic additions. The discussion of alkene reactions will continue on in section 4 of my video. Okay. So let's change gears, and now let's talk about the reactions of alkenes. We've seen 3 ways to make alkenes: elimination, Wittig reaction, and the reduction of alkynes. Let's talk about the reactions that alkenes do. They do essentially 4 types of things, and we'll go through each of these in turn. I want to convince you that the first 3 are actually close variations. So there's really only 2 major types of things alkenes do, but obviously things are going to be more complex than just this, so there's going to be some different variations on these themes of electrophilic addition, cyclopropanation, etc., cycloaddition, and reduction. But let's just start with electrophilic addition. If I react an alkene with HBr, I will achieve a product, which if you look at this is an addition, because I've started with something from the organic standpoint that's C6H whatever, C6H12, and I've formed C6H13Br. That is, I've added an H and a Br. So how does this happen? Well, HBr is an acid, and we know that an acid, the Bronsted-Lowry definition of an acid, is it's a source of proton, H+. So you got H+. H+ wants electrons. Who has electrons? Well, it's going to be the pi bond, because that's going to be the highest occupied molecular orbital. That is, that's going to be the electrons most available for reactions. So let's imagine the pair of electrons that are shared between these 2 carbons reach out to instead be shared between this carbon and this hydrogen. So this pair of electrons reaches out to here. Of course, hydrogen can only have 2 electrons, so let's break a bond, have bromide float away. If I make a connection between this carbon and this hydrogen, using these 2 electrons, this carbon lost electron density in the deal. So we got a carbocation here, right? This guy wants electrons. Who has electrons? Well, bromide has electrons. And so there we go. That's our reaction for an electrophilic addition. Pretty straightforward. A lot of reactions of alkenes follow exactly this scheme. For instance, if we take the same alkene and react it with HCl, well, we do the exact same mechanism. There's really no difference between this and the previous reaction. It's just chloride instead of bromide, so no big deal. We could do the same thing with aqueous acid. Okay, let's imagine we've got my alkene and aqueous acid. H3O plus, the hydronium ion, is a source of H+, so let's have our pi bond reach out to H+. We make the exact same carbocation intermediate. Now who has electrons to share? Well, it's water. So let's water molecule come along. Now we're not quite done. This is going to be just a little bit different than the previous example. Notice pi bond reached out to electrophile, acid, carbocation intermediate, and some nucleophile came along. Here we're not quite done just because this species is not neutral, but generally speaking, if you've got an intermediate that's positively charged, you can get back to neutral just by deprotonating. So let's imagine something. Let's say another water molecule comes along and picks up that hydrogen. And what's our byproduct? An alcohol. So we've added an H and an OH across the double bond. Except for this last little bit of just kind of cleaning up by pulling off a proton. Notice that the mechanism here is exactly the same as the mechanism of HCl and HBr. That is, its pi bond reaches out to electrophile, Lewis acid, electron acceptor, carbocation intermediate, and then a nucleophile, a Lewis base, an electron pair donor, comes along. We could generalize this process. Let's just imagine a whole series of reactions that are just different combinations of electrophiles and nucleophiles. That is, pi bond reaches out to electrophile, carbocation intermediate, nucleophile comes along to give addition product. Okay, in those previous reactions, I used symmetric alkenes for all of them. I used 2,3-dimethyl-butene for all of those. And they're symmetrical, so it didn't matter where we put the hydrogen and the bromine, for instance, if we used HBr as our agent. But what if we had an unsymmetrical alkene, for instance, 2-methyl-2-butene? Here, there's two potential isomers of product. I can put the H here and the Br here, or the H here and the Br here. That is, I could form, as shown, the blue and green products, and they're isomers of each other. And it turns out that we only form one. So let's see if we can see how. The mechanism involves first pi bond reaching out to the electrophile to make a carbocation intermediate. Okay, if we connect the hydrogen here or here, we're going to get two different intermediates. So if we connect the hydrogen at this position, we'll form the green intermediate. If we connect the hydrogen at this position, we'll form the blue intermediate. Now the green intermediate involves a tertiary carbocation, and the blue intermediate a secondary carbocation. Tertiary carbocations are much more stable than secondary carbocations, and so the green intermediate will form preferentially. Therefore, the green product will form. Okay. Now, I just did want to remind you there are reactions that give the opposite selectivity, but that involve where you react HBr and you get the opposite selectivity, but that involves a radical process. We mentioned this briefly when we talked about radical chemistry. I don't want to go through this right now, but if you've got a different mechanism, you're not going to necessarily get the same same type of selectivity. So the different product really suggests that something else was going on here, and some careful analysis led researchers to realize that it was a radical process. But electrophilic additions are going to go with this sense of selectivity such that the electrophile ends up going to the less substituted position and the nucleophile to the more, because you go via the more stable carbocation intermediate. All right, so let's look at some other reactions, addition reactions. If I react an alkene with a high concentration of, say, Br2 or Cl2 or I2, I'll get an addition where we add bromines to either end. Now this is, again, an electrophilic addition, so who's my electrophile? Well, it's one of these bromine atoms. Br2, yeah, bromine, we often think of it as a bromide, but this Br2 is, if we could break off a Br minus, what would be left would be a Br plus. There's not really Br pluses floating around in solution, but one end of the Br2 can act the electrophilic end. So imagine we've got a Br2 and we've got some weak nucleophile, like a pi bond, can act as a weak electron pair donor, can reach out to make a bond to bromine, kicking out this really good leaving group, Br minus. And that'll make an intermediate, this carbocation intermediate. But this is going to be a little bit different than our previous carbocation intermediates. In our previous examples, the electrophile was an H. Those examples all used acid and Bronsted-Lowry acid as the electrophile. But here, our electrophile is a very large atom. It's not a hydrogen, which is very small. It's a very large atom. So it takes up a lot of space, and it's got lone pairs. And it's right next to this thing with a positive charge. And so you might imagine these lone pairs, because this picture really is misleading. This bromine should take up a lot of space. And these lone pairs are really sitting very close to this empty p orbital, the carbocation. And so you could imagine a pair of electrons interacting with that empty p orbital to make this structure. And that's really a resonance form. The real thing is an average of, well, not just these two, but a third, because I could also imagine breaking this bond and making a third resonance form. And the real thing is actually an average of these three structures that has some positive charge. It's really got a bridged structure where there's carbon, bromine, and carbon forming kind of a bridge. And there's some amount of positive charge on each of our carbons. And then our bromide comes along and adds. But when our bromide comes along, this thing, I've implied that this is all planar, but it's not. Because in my intermediate, I've got that bridged intermediate, as I showed, and it's stabilized. That bromine is really kind of on one side of the ring and not the other side of the ring. right? It's not planar as implied by this picture, which really leaves off any stereochemical indication. It's on one side of the ring and not the other side of the ring. And this bromine is a large group that's essentially blocking this face of the ring. So the other bromide is going to end up coming not from down here, but instead from above. And so what we're going to get is an anti-addition product. This bromine is going to always come from the opposite side of that one. Now I'm going to get a 50-50 mix. So I'll get some where this bromine is forward and this one back, and others where this one is back and this one's forward. So that's a racemic mixture. But it's going to be an anti-addition product. Oh, here I showed the arrows. Okay. Let's take a little baby step from the bromine addition. If I take bromine and water, I get a different product called a halohydrin. Don't worry so much about that. But where I've got a bromine and an OH group anti to each other. Racemic mix of this. Now this should look a lot like the previous reaction, and in fact really behaves like the previous reaction. If I have my alkene and I've got R2, my pi bond reaches out to bromine, kicking out a bromide minus, to make this bridged intermediate. But if I've got a lot of water around, for instance, if my solvent is water, so if I've got a little bit of Br2 and a lot of water, yeah, there's bromides, and a bromide could come along and add. But I could also have a water come along and add. And if I've got a great excess of water, that's going to be more likely just for statistical reasons. And if the water comes in and adds, it's going to come from the opposite side. There's going to be an anti-addition to make an intermediate, and then after loss of a proton, we're going to form a 50-50 mix of this and the mirror image of this, of the two enantiomers. Okay. Now I'm going to show another reaction that if I just show this overall net reaction, it looks a little different. But I'm going to try and show you that this really behaves, this is really a lot like the one I just showed you, where I had Br2 and water. Because if I take an alkene and I treat it with mercuric acetate, we'll talk about what that is in just a second, and water, followed by sodium borohydride, I am going to get the net addition of a hydrogen and an OH across this bond. What is this mercury thing? Mercury with two acetate groups. These are acetate groups. OAC means an acetate. It's an acetate, this is an acetate, is your acetate ion that you learned about when you learned about polyatomic ions. It's the conjugate base of acetic acid. And it's a resonance stabilized anion, and so it's relatively easy to break this bond to make a positively charged mercury and the acetate ion. Now this is an equilibrium, so this will come back on, and maybe this other one will break off. But at any given time, we've got some amount of positively charged mercury if I've got a solution of mercuric acetate. Well, that's going to be a good electrophile. And so if I've got a pi bond, that pi bond is going to reach out to my positively charged mercury. But like bromine, I'm going to make this carbocation intermediate. But like bromine, mercury is very large, and it's got lone pairs. And so I'm going to form, as we saw in the case, a bridged intermediate. So the real thing is going to be actually an average of these. But it's a weighted average. And since of these three, this is the most stable individual structure. Like if I imagined that resonance didn't happen and I've just got three separate structures, this one is a more stable structure because it's got a secondary carbocation than this one that has a primary carbocation. So my weighted average actually looks more like a secondary carbocation than it does like a primary carbocation. So yes, there's partial plus on each of these two carbons, but there's more partial plus on this center. And so a nucleophile, if it comes along, is going to add to this center. And by the way, it is with anti-stereochemical orientation. This particular example show that off. But if my nucleophile is water, I can add at this position, and loss of a proton will make this OH and mercury addition product, where the mercury was the electrophile and the OH from water was the nucleophile. So notice I still added electrophile and nucleophile on these two positions, Markovnikov is still dominating here. But the overall product I showed before didn't have mercury in it. Sodium borohydride, I'm not going to go into this in detail, but it's a source of H-, and that H- will get together with the mercury and then do a what's called a reductive elimination to put a hydrogen where that mercury was, with retention of stereochemistry at that center. So we end up with a addition of hydrogen and hydroxyl across a double bond in such a way that the OH is at the more substituted position. Now you might say, why bother using this mercury species? Because that's the same thing we predicted from just acid and water, right? H would add to one end and OH would add to the other end. Well, the reason to bother is that in the addition of just acid and water, you form a discrete carbocation intermediate. That is, at one point of the game, your product would look like this. But this carbocation intermediate is actually prone to rearrangement. That is, this is a secondary carbocation. And if I just move this hydrogen with 2 electrons, if it just shifts just a little bit over this way with those 2 electrons, I have a tertiary carbocation. Remember, hyperconjugation, the stabilization of carbocations by adjacent CH bonds, is essentially this. It's electron density from the adjacent CH bond being shared. But you know what, if that's shared, a lot, ultimately, I get this, not that. If basically these electrons are preferred to share with this. And since I make a more stable carbocation, this hydride shift, this hydrogen with 2 electrons shifting over one position over, is a pretty reasonable thing to do to make a more stable carbocation. Actually, if I did an SN1 reaction, well, I know how those work, right? If I started out with this alkyl halide and I just treated it with water, which is a weak Lewis base, let's say I heated this guy up, leaving group would leave to make a carbocation. Which carbocation? This carbocation. And then if water added at that point, we'd make this. If we pulled off a hydrogen from the next position over to make an elimination product, we'd make this. And you recall from Chem 2 that when you have SN1 and E1, those go hand in hand. You're going to generally get a mixture of SN1 and E1 products. But in addition to those two, which you might have expected, we also get this. Well, what's this? This is the result of rearrangement of this sort, because if we make this type of intermediate, it can rearrange to this carbocation, and then if water attacks, we get this. In reality, in lab, if you take this and heat it up with water, you're going to get a mixture of these 3 products. We can play with the conditions to get a little more of one or a little more of the other, and actually as you alter some of the conditions, you'll kind of push it a little more one way or the other. But still, you're going to get a mixture of products. What's the lesson here? Carbocations can rearrange, and when they rearrange, you can get unexpected products, or you get a mixture of products if some of our molecules rearrange and others do not. Well, if I treated an alkene, such as this, with just acid and water, right, H3O+, I'm going to get some of my expected addition product, where I get H and OH on these 2 positions, respectively. But I also get some other product. Well, why did I get this? Because along the way in the mechanism to make this, what happens? First pi bond reaches out to H, you get a positive charge here. If water adds at that point, you get this product after loss of a proton. On the other hand, it can happen that a hydrogen can shift over one position, as shown at the top of this slide, to put a positive charge at the tertiary position. And then if a water molecule attacks after loss of a proton, we make the 2-hydroxy 2-methylbutane. Okay, so just acid and water gives us a mix. But oxymercuration, demercuration, that's what the name of this process, where pi bond reaches out to mercury and water, I guess I should have water written down here, and water adds, and then sodium borohydride gets rid of the mercury, we end up with the other isomer. What would this be? 2-hydroxy 3-methylbutane, or I really should say 3-hydroxy 2-butanol would be the proper IUPAC name for this. Why does this one only form one product and this one forms two? Because the carbocation intermediate in this case is stabilized by resonance. That bridging resonance where in the intermediate the mercury is bridging these two carbons makes that intermediate stable and it doesn't rearrange, and so then as water adds you end up getting this product. So we've seen that you can do a reaction that adds H and OH that puts the hydrogen on the less substituted end and the OH on the more substituted end. That's Markovnikov. Oh. Now I just wanted to point out that you don't have to use water as your nucleophile. This reaction works by pi bond reaching out to electrophile, which is mercury plus, to make a bridged carbocation intermediate, and then a nucleophile, water, comes along. And then part B, the sodium borohydride basically replaces the mercury with a hydride to make H and OH. Well, we can do a variety of different reactions. For instance, instead of using water as our nucleophile, if an ethanol was our nucleophile, OET would end up adding at this position. ET just means ethyl. And so instead of making an OH, an alcohol here, we'd make an ether, where we've got some O carbon-carbon-carbon group, depending on what alcohol we used as our nucleophile. The mechanism for these two reactions is identical. It's just instead of having water attack, you have ethanol attack. But still, you've got lone pairs on these positions. And it's the same arrow pushing. Our next reaction is going to initially look wrong, because in all of our previous examples, we always put the H on the less substituted end and the OH or other things on the more substituted end. And in fact, that's what Markovnikov originally observed. He did a bunch of acid reactions, and he observed that the hydrogen goes to the end that starts out with more hydrogens. Okay. Mechanistically, we know that that comes from the pi bond reaching out to the electrophile, carbocation intermediate, and then a nucleophile comes along. And by the way, it's Markovnikov's work that helped us elucidate the mechanism. That's how we figured out what the mechanism was. Markovnikov and other people's work on the fundamental reactions helped us understand what was going on. But this reaction that I've shown here, an alkene treated with first borane, BH3, followed by basic hydrogen peroxide. So you might see this written as H2O2 and sodium hydroxide. I will write it as the hydroperoxyl anion, HOO minus, because that's really the active agent. Excuse me. This reaction appears to give the wrong result. It puts the hydrogen on the more substituted position, in violation of Markovnikov's initial observation. But here, our misunderstanding really lies in what is the electrophile. And I'm going to draw this like we drew our previous reactions. And this is a lie. I'm lying to you right now. This is not how it happens. Can I be more obvious? I'm going to show you in a moment that it all happens in one step. But imagine our pi bond reaches out to the electrophile. Borane, BH3, this has an empty p orbital. Neutral BH3 has an empty p orbital on boron. And this boron does not have a full octet, and so it wants to act as a Lewis acid, an electron pair acceptor. So pi bond can reach out to boron to make a carbocation intermediate. But this intermediate, notice it has a boron with a negative charge, because boron with 4 bonds has a formal charge of -1. And so boron's a little bit schizophrenic. On the one hand, it wants extra electrons because it wants to get to a full octet. But if you have a full octet, now you've got a negative charge. And remember, stability lies in the balance between the octet rule and the balance of charges. And here, boron, with a negative charge, it's relatively easy to break one of these bonds and have something go away with its 2 electrons. You have seen, for instance, in the past, BH4 minus act as a H minus source in adding to a ketone. So this can act as a source of H minus. So let's imagine giving off an H minus, but where could that H minus go? Hey, right next door, we've got a positively charged center. So let's imagine a hydrogen with its 2 electrons hopping right next door to this positively charged center to make a hydrogen here and a boron here. Now, in reality, it does not happen in a wise fashion like this. In reality, the orbitals all line up such that the pi bond reaches out to the boron, and simultaneously, this BH bond, those electrons get transferred back to this carbon. So there's one transition state that is delocalized. That is, all these bonds are forming and breaking simultaneously to make this addition product. Now, it seems like we're violating Markovnikov, because Markovnikov says the hydrogen goes to the, Markovnikov originally just observed that the hydrogen went to the less substituted end. But our mechanistic understanding of Markovnikov's observations was that it's the electrophile that goes to the less substituted end, because you want to make your carbocation at the more substituted position of our 2 possibilities. Well, here, yeah, it happens all simultaneously, but there is some amount of positive charge buildup in the transition state, and it would be better here than here. And so boron's going to go to this end, and here it's H minus that goes to this end. So the reason that this doesn't follow Markovnikov's initial observation is that Markovnikov said hydrogen goes to the less substituted end, but really it's the electrophile. And in this case, hydrogen is not the electrophile. It's not H+, it's H-. So usually hydrogen, in reactions we've seen, yes, we saw lithium aluminum hydride and sodium borohydride reacting with ketones, but usually we've seen hydrogen as an acid. But here, hydrogen is the Lewis base. So that's why this overall select seems the opposite. To get all these orbitals to line up, notice that in the transition state, we've got the carbon-carbon double bond, that pi orbital, so made up of these p's. We've got the boron p orbital, and we've got the sigma bond between boron and hydrogen. And to have these all interact simultaneously, this and this interacting, this has to happen in a syn fashion. Because my electrophile and nucleophile, my boron and hydrogen respectively, are attached to each other, they cannot be simultaneous, and it all happens simultaneously. They can't be one up here and the other down here. So this reaction has to go with an addition. So for instance, if we treated 1,2-dimethylcyclohexene with BH3, both the boron and the hydrogen would either come from the top or they would both come from the bottom. And then after treatment with basic hydrogen oxide, the boron would be replaced by an OH. So the OH and the hydrogen would be syn to each other. This is a syn addition reaction. I am not going to belabor how this happens because I really want to focus on what's similar and how we can understand the reactions of alkenes to pretty much go with this pi bond reach out to electrophile, nucleophile adds to the other side motif. But the second half of this reaction, the borane, when it's treated with basic hydrogen peroxide, the boron gets replaced by oxygen. Here I show the mechanism for that process. I won't go through this in depth. I won't hold you responsible for the second half of this process in any depth at all, aside from knowing that the basic hydrogen peroxide replaces the boron with an OH. Here's how it happens. You can look through this at your leisure. Okay, let's sum up a series of reactions. If I treat this same alkene with acid and water, this should be H+ and water, oxymercuration, demercuration, or hydroboration oxidation with 3 different sets of conditions. The first one's going to add H and OH in a Markovnikov fashion, but there is the potential for rearrangements. Particularly in this case, our initial carbocation at a secondary position could lead to a tertiary carbocation pretty easily. You're going to be relatively likely to see a rearrangement. On the other hand, oxymercuration, demercuration gives us the apparently Markovnikov product. That is, the hydrogen goes to the less substituted end, and there's no rearrangement. And this oxymercuration, demercuration, sorry, that was that one. This hydroboration oxidation process, this should be HOO- by the way, gives us the opposite regioisomer That is, it puts the OH on the less substituted position. This is sometimes called the anti-Markovnikov product because it goes the opposite of Markovnikov's initial observation. Now, we know from our discussion that this really isn't violating this electrophilic addition mechanism. It's just that the hydrogen in this case is the nucleophile, not the electrophile.